For the second order system, now GS is and also we can look at the similarly, and then we are looking at GJ omega, and then S equals J omega. So for the second order system, we can do this similarly. What you can do is that you can actually divide by omega n. So look at the when the omega is very, very smaller than omega n, which is maybe 0.1 omega n, and the omega is almost the same as omega n, and the omega is larger than omega n. So the G, the magnitude G, when the omega is very smaller, omega is very smaller than omega n, GJ omega is almost the same as, well, in that case, this and this can be almost ignored. So therefore, we have omega n square is 1. When the omega is almost the same as omega n, then we have only this part, because these are cancelled out. Then what happens is that J omega is actually let's plug in everything. 2 zeta omega n square times J omega n plus omega n square the omega n square, and then these two are cancelled out, and then actually this will be the omega n, and then this will be the cancelled out. So the magnitude is nothing but 2 zeta. And when the omega is much, much larger than omega n, it becomes G. Sorry about this brief interruption. Hope that helps to wake up. It was my kid. So GJ omega, the magnitude now, the other part is almost negligible. So then it becomes 1 over omega square. And then let's look at the angle. So when the omega is very small, other part like this part, is negligible. So we have the angle, there is no almost 0 phase delay, so it will be 0. When the angle is the same as omega n, we can still use the same equation, but now the angle, looking at the, now we are looking at the angle. So then it will be angle of 1 over 2 zeta j. So I'm still using this equation. So then it will be negative 90 degree. And then when the angular omega is very larger than omega n, then similar to the magnitude, other part is negligible. So we have Oops. Something like this. Then also another characteristic is that because now we have omega n square, means that the decay level will be negative 40 decibel for decade. And then actually we didn't look at the actually log magnitude. So 20 log G, therefore for small and small frequency is 0 because log 1 is 0. And then for this 20 log 1/2 zeta will be minus 20 log 0.5 minus 20 log zeta. And for here, 20 log 1/square becomes minus 20 log omega square, becomes negative 20 log omega. So this makes negative 40 decibel decrease per decade. So we have now log magnitude plot, log magnitude, and then angle. So we are ready to draw body plot, which is log magnitude and phase. So again, I make, so small means that 10 times smaller, the large means that 10 times larger. So let's make something like this. 1, 2, 3. And then x-axis is log omega. And then the first y-axis is 20 log G, which is magnitude, and this is angle. From the log magnitude part, let's use green. So when the omega, actually this should be 0.1 omega n, and then omega n, and then 10 omega n. This is very, very small, means that 0.1 omega n, and then some n the same, and then large means that 10 times larger. And then when it's very small, the magnitude is, this is 0, log magnitude is 0, and when omega n is almost the omega n, omega is omega n, the input frequency is almost natural frequency, then it is depending on, the amplitude will depend on the zeta. And then the zeta is typically smaller than 1. So if the zeta is 1, then it will be here. But if zeta is the typical damping ratio, it will be going up. So the higher amplitude means the smaller zeta. And then this is maybe typical zeta, and the magnitude will go up depending on the damping ratio, change it depending on the damping ratio. And then when the omega is very, very large, then it will decay at negative 40 decibel per decade, which we found just before. And the angle will be also changed. Then for the angle, let's do this. When the omega is very small, angle is 0. So it will be here. And then when the omega is natural frequency, it will be negative 90 degree. And then when the omega is very large, it will be negative 180 degree. So it will start from here and then go to there, or in between can be, looks like it can be something like this, or can be something like this. It depends on the damping ratio. So if the damping ratio is small, so this is for small damping. The angle will be changed very quickly. It's very intuitive. But if the damping ratio is large, the angle will not be changed such quickly. So this is the example of a body plot for typical first order and second order system.